So, good afternoon, everyone. We are the Accelerated Class for AI AutoML team. My name is Ki. I'm here with Ruben and Ju today to present you our work in this past year. So let me first provide some context on SI. SI is a system that provides solution to machine learning modeling on cloud. It has three main components, including AutoML, execution engine, and data lake. Our project mainly works with the AutoML component, but all of our jobs run in the context of the whole SI system. There has been a lot of previous work in the field of AutoML. For example, there are AutoWake and AutoScaLearn. Both address the problem of combined algorithm selection, hyperparameter optimization. However, both toolkits do not use distributed implementation when running the jobs. There's also the Azure AutoML, which is a cloud-based service for building end-to-end machine learning pipelines, which is pretty helpful for both experienced and no-code experienced users. And lastly, there is WMB, which is an experiment tracking platform with strong visualization dashboard that can be integrated with most of the most popular ML frameworks that we've seen. However, as far as we know, currently Azure AutoML does not support customized models. And WMB, although it has a model registry, it does not support explicit model selection, model comparison. So our proposed solution evolves around the AutoML orchestration engine. On a high level, it takes in the user input, it conducts pipeline optimization, submits the jobs to the lower level SI system for execution, and it also completes automatic logging and bookkeeping. And our scientific hypothesis can be viewed from three main perspectives. So SI AutoML is able to identify the pipeline configuration that use similar or even better performance than human expert tuned models. It is also going to save both time and cost for the user. And also to briefly mention the intended users for our system, we consider that any ML practitioners who wants to experiment with their pipelines can submit their code to AutoML for an automatic experimentation. And we've also been working with QA researchers who have been suggested and who have been suggesting and providing QA pipelines that are built into our AutoML system, which we consider to be a pretty good platform for future students to explore different phases of the pipeline and possibly test out their own idea.
So next, I'm going to briefly introduce the system functionality, as this is mainly the same as the spring semester designs. So the components include a pipeline descriptor and the orchestrator, and also ideally a resource provisioner, but we put this into later work because some technical issues and the constraints we had during the development. And also there are components, model explorer, data selector, and hyperparameter tuner. These are the non-functional requirements, most of which we can accomplish with only some bullet points into performance. Due to the same technical restraints we have, we weren't able to benchmark and guarantee some of the requirements. And this is the resource requirement. First, a lower level system and the code implementations of existing machine learning models, and also a complete machine learning pipeline description is need to be developed. These are the design considerations. Most of them are very straightforward. And the system requirement, we need the lower-end SI system, also base environmental Python 3.8. This is the system design architecture figure. This is also the same as the last semester. So SI AutoML are integrated as a part of the entire SI system. And this should communicate with the lower end system through the SI SDK. And for data design, first we need a user input data, which should consist of a machine learning pipeline in the form of a YAML file, as well as the data set and the machine learning code that the user defines. And the pipeline should consist of phases, which phases should consist of modules. And module contains all the relevant information that is for a subtask. And also, we need to keep locally previously executed models table for easy query into the names and types of the model, as well as the accuracy and the training time. And there is also an internal duplicate job model that is for duplicate job detection purpose. This implementation overview, I'm also going to briefly introduce that because that's also the same as the spring semester. So first, user submits the AutoML task to the user interface, and then the orchestrator launches the task for the pipeline descriptor to read in the YAML file and generate the machine learning pipeline. And then the orchestrator plans the optimal execution path depend on the pipeline object and launch the assign job procedure, which I will introduce later. And the orchestrator then monitors the job performance and provides the final results to the user in the end. And for assign job procedure, it's a combined execution of the data selector, model explorer, and the hyperparameter tuner to actually configure in the configuration space of the machine learning pipeline to launch the actual parallel jobs to the backend to execute. And for resource provisioner, this hasn't been implemented even though it is in our plan in the spring semester. This is mainly because of these issues. First, we have limited access to a lower end size system resources information. And then we have had a limited ability to provision, modify, or keep the resources at the backend. So it is proposed in the future work in the hope that through efficient communication with the system team, we can gain more support on the interface part.
Coming to the design models. So first off, we have the duplicate job detection algorithm. And this was also we implemented in the spring semester with some modifications made to it so that the other components we implemented in the fall semester, it's consistent with it. The whole idea behind the algorithm is that since machine learning is a highly iterative process, there are many, when a user submits multiple pipelines over time, many of the components are the same and they need to be re-executed. So we can skip that execution and we can save quite a lot of time. So that's basically what the algorithm does. And the way we do it is basically we create a hash of the module properties and we just store that hash in the DB and check whether it's going to be there or not every time we run a job. And this helps us save quite a lot of execution time. The hyperparameter tuning is also the recursive subspace exploration technique, and this was also developed in the spring semester. The main idea behind the algorithm is that a grid search is too slow, and for a distributed implementation, we found this algorithm to work well. So what it does is it initially takes very large steps to cover the big search space that you have, and then it finds optimal subspaces, and then it takes smaller and smaller steps in those subspaces. So it recursively shrinks the subspace it looks at, and it kind of saves quite a lot of execution time. And for the experiments that we ran, it kind of identified similarly optimal models as well. So the model selection is one thing that we did in the fall semester. That's basically the ability of Asai AutoML now to accept multiple ML models from the user. So before the user could submit only one ML model, now we can submit multiple ML models, and AutoML would basically execute each of them, find their optimal hyperparameters, and return that to the user. But now, since we're searching over the model space as well, the search space is really big. So we also developed the model subset selector algorithm. What the algorithm does is it helps us to reduce the model search space in a way. The intuition behind the algorithm is that, for example, if you have a task, say the classification task, and if you have a type of data like the biomedical data, if I know that a particular model did well for a biomedical data set more than other models that I ran before, it's very likely that if I have a new biomedical data set, this model itself might beat the others. So we kind of use that intuition to kind of reduce the search space. And that's what we do. It goes through, so when the user provides a list of models, we go through them, we take each model and we say, have we run this before for the same task and data type? If we have, out of the set of models that we have run before, we only select the top 2 of them. And then this along with the new models is what we run this time. So that saves us quite a lot of execution time. The idea behind this is pretty good, but our implementation right now is a little bit naive with a lot of string comparisons, but this is something that you can improve upon really well in the future as well.
And then we also added a data selector component. The motivation behind is that when having a very large model with a large data set, we probably want to tune the model first using a subsample of the original data set, and then apply the best configuration on the full data set, because there might be constraints on time, on computing costs, and sometimes it's just infeasible to tune the whole pipeline on the full data set. So with the data selector, the major change is in the execution order. Now we will be running the same pipeline twice. In the first round, the data selector will be generating the subsample using a random sampling strategy based on a subsample percentage specified by the user. And then it's going to pre-process that subsample file and do the model tuning with the subsample. And then by the end of the first round, we'll be saving the best model and hyperparameter configuration to a temporary file, which will be used in the second round. And when we get to round 2, we'll now be working with the full data set. So we'll be pre-processing the full data set. And then when we get to the modeling module, we'll first read the best configuration from the temporary file that we generated in round 1, and then directly apply that on the full data set. So by round 2, we'll be getting the final result. And then we also added a multiple preprocessing explorer functionality, which allows the user to specify different preprocessing strategies they want to test out in the YAML file. And then for each of the preprocessing strategy, the orchestrator will be executing a task respectively and output the results respectively, so that the user can make their own judgments on which preprocessing strategy seems to work the best. So that's for our design models. And then for test design, we ran an experiment to evaluate the performance of each individual components that we mentioned earlier. And we also compared against an industry AutoML system called AutoSKLearn. We reported the results in terms of both the model performance and runtime. And later in the results section, we'll discuss those in more details.
And this is the deployment model. So this is also the same as the spring semester, with the only addition being the standalone databases, as mentioned in the data requirements. We need a model databases and also a duplicate job detection databases as standalone databases. Now we deploy them on GCPs. And ideally, all the models should run, all the resource services should run as a different standalone microservices for scalability and fault tolerance. But currently they are run on a monolithic service under the cloud. And each of the services is defined as classes in the whole project. And hope in the future, this will ease the migration effort that it will take to put everything onto separate microservices, because it has a clear definition of individual classes. And for development model loci, this is also our work in the spring semester. It is mainly for the purpose of speed up the development of hyperparameter tuning and duplicate job detection, and provide the local developing environments that will mimic the behavior of the lower-end SI systems. And we hope it formulates a detailed API extension to lower-level SI system and saves a lot of budget and time on our side.
So coming to the risks and challenges, the main one is that SI AutoML might not identify a reasonably optimal ML model, because we always balance execution time and performance. So in this case, it would cause performance degradation and cause loss of user revenue as well if you don't give the user the optimal model. But the other one is that if we have two similarly performing models, AutoML does not return the one that uses lesser resources, and that would cause wastage of user money. The other one is that privacy issues that we have, because we for duplicate job, we kind of take a hash and over the data, we kind of go over the data in a way. So that can lead to privacy issues with certain data and models. This is the tools and dependencies that is needed. And the main one is at the lower level SI system. And for AutoML, it's the libraries Python, the request library, the PyYAML pandas library, as well as the user data and the model that the user needs to give it to us. Quickly going through the tasks, in the spring semester, the main ones that we weren't able to do is the metadata logging and the error handling functionality. And these are mainly to give the user a better experience of working with the AutoML system. The main reason why we pushed this is because of time constraints and also certain issues that Gio will talk about later. And the other main thing is the resource provisioner. Again, this is because of the reasons that Gio mentioned earlier. In the fall semester, we were able to maintain hit like most of our goals, other than implementing additional hyperparameter tuning strategies. We spoke about this with Professor Nyberg as well, and there were a couple of issues because like Bayesian optimization is sequential, and we had like a distributed implementation, and we kind of selected to focus more on adding more features like the multiple pre-processing stage features. So that's another thing that we didn't do. This is the milestone plan that we've linked as well. And this is a detailed milestone plan linked. So just a recap. So right now, the state is that a user can submit a YAML file to SI AutoML. And in this YAML file, we specify like the modules that the user wants to explore. So for example, like a pre-processing module and a model module. Now, in the model module itself, the user can specify multiple ML models that he or she wants us to explore, and each with different hyperparameters and different hyperparameter tuning strategies as well. And also, if he or she wants to explore multiple pre-processing strategies, we allow that as well. So the first results that we have is for the duplicate job detection as well. And this is similar to the ones in the spring semester. In the spring semester, we ran it on LaSai, and right now we run it on ASI, and we see similar results. So in this result, we have one pipeline which uses the squad data and the a pre-processing module A and a model module B. And we also have another pipeline which on the same squad data uses the same pre-processing module, but a different model module. So when we run this with duplicate job detection on the table on the left, when we run pipeline 1, both the modules run and gives an execution time of 585 seconds. But the moment we run pipeline 2, it realizes that we've run a pre-processing module A on squad data again. So we skip it and we save quite a lot of time. And this is something that's really useful. And you can see the results in the AutoML experiment as well, because as we run it, it kind of saves time quite a lot. In terms of hyperparameter tuning as well, again, similar to what we observed in the spring semester, even on ASI, the recursive search is much faster, and it's able to identify the same model as well. So when we used it for the candidate answer BM25 model on the squad data set, as opposed to grid search, it is much quicker, and it's able to identify the same values as well. And even in the AutoScaler experiment, it kind of identified better values than Bayesian optimization much quicker as well. The model selector results is basically just to show that ASI now does support multiple models. So we submitted 5 different versions of the BM25 model, each on an exclusive range of hyperparameters, just to mimic them being different models. And so basically, it goes to them, it finds the optimal hyperparameter for each model, and it returns BM25 V1 to the user because that had that highest test MAP. To demonstrate the performance of the model subset select algorithm, basically what we do is, once we do run BM25 V1 to V5, we then submit BM25 V1 to V10 for the same task, which is QA, and for the same type of data. For this time, it's the field, we just named it squad. So without the data selector, it kind of runs all of them again, and it gives a total time of 4,000 seconds. But with the data selector, it identifies that, okay, I've run the first 5 models, V1 to V5, on the same task and data type before. So what I'm going to do is I'm just going to select the top 2 performing models, which correspond to V1 and V5. And I'll run these along with the new models, which is V6 to V10 again. And this helps us save a 28% execution time as well.
Okay. And for the data selector experiment, we use a different QA pipeline, which was adapted from the original Hugging Face script. It contains a simple preprocessing module and then a model module, which applies a BERT tiny model on the SWOT dataset to conduct answer extraction tasks. And due to the constraint in time, we only tune one hyperparameter, which is the invest size. And then we tune a model for 10 epochs using the default learning rate. Another thing to point out is that we only sampled 5% of the original squad dataset to use that as the full dataset in our experiment. And with data selector enabled, it further takes 20% of that dataset as the subsample. So from the result, we can see that with and without data selector, both trials selected the same hyperparameter value, resulting in the same test F1 score. But when it comes to the time, without data selector, it takes about 2 hours to complete the whole pipeline. But with data selector enabled, meaning that we first tune the model using the subsample, then apply on the full data set, the runtime got reduced by about 30 minutes, which was about 27% time reduced. So we will claim that with a much larger search space and a larger data set, the data selector component will be very beneficial for the whole pipeline tuning experience. And then we also showcase a usage for the multiple preprocessing explorer, where the user wanted to explore 4 different preprocessing strategies. And the results here just presents the hyperparameter value selected, the test MAP, and the time taken to run each of the tasks. And last but not least, we also compare against AutoScaler, which is an industry AutoML framework that supports classification and regression tasks using the model supported by scikit-learn package. We focused on classification tasks in this experiment by selecting 4 classifiers: decision tree, gradient boosting, random forest, and k-nearest neighbors. We apply those on the UCI breast cancer dataset, which It's a pretty small but classic classification data set. And from the result, we can see that Asai AutoML actually outperformed AutoScaler both in terms of test accuracy and time. So basically, it was able to identify a better model within a shorter amount of time. And then we'd like to discuss more on the comparison between Asai AutoML and AutoScaler. We would say that one of the strengths of Asai AutoML is the flexibility it provides. Basically, it can support any task, user-specified model, and data preprocessing strategies, whereas AutoScaler is more bounded to the ones that are supported by the scikit-learn package. And then Asai AutoML also support distributed implementation. We run jobs parallelly, giving a faster performance. And another key difference is in the pipeline optimizations. Asai AutoML employs recursive hyperparameter tuning strategy, whereas AutoScaler use the popular Bayesian optimization, which theoretically should have identified better models with unlimited resources, but unfortunately not in our experiment setting. And also lastly, we would conclude that Asai AutoML is more suitable for people who have some coding experience because they'll need to write their pipeline and submit to AutoML, whereas AutoScaler is more user-friendly for a beginner to machine learning because they only need to call on the API, AutoScaler API, which is pretty simple.
And then we will jump into the performance analysis section. So in this section, I'm going to look into the detail of some of the time profiling of the machine learning execution pipelines that we have run. The first one being a BM25 model and squad dataset, as mentioned earlier, with recursive search hyperparameter tuning algorithm. So for the x-axis, it's the execution time from the beginning of the pipeline. And for y-axis, these are the different pods on the Kubernetes cluster backend. And also for the top one with the blue bar, that's the module execution time. And for the orange and green bars, these are the actual individual jobs. And the orange bar indicates the, oh, sorry. Yeah, the orange bar indicates the wait time. That includes the time waited for the pods to be placed on the Kubernetes cluster and the time to download the container image and install that, and also the time to install system dependencies for those jobs. And the actual green time is the user executed code, including custom libraries installation, and also the actual execution. And you can see that here, Asai AutoML utilizes the parallelism that is provided by the Kubernetes cluster at the backend to launch as many parallel jobs as possible to shrink the execution time. And it is something that we cannot enjoy from the or single cluster as a single node execution. But one important or interesting factor that we noticed is that for small and frequent short-lived jobs, actually the job preparation time is relatively significant compared to the actual execution of our pipeline. So for example, in this figure, in the very last column, you can see that the preparation of the pods is actually almost as long as the actual job execution. So this prevents Asai AutoML from launching frequent short-lived jobs, such as the resource provisioning jobs, in terms that it will waste a lot of time in terms of actual job preparation. And the second part is providing about the data subsampling. And the x-axis and y-axis are the same as the last slide. And on the left, it is the providing without the data subsampling, meaning that it is a grid search on the entire full data set. And on the left, it is with the data subsampling, meaning we first hyperparameter tune on the 20% data subsample, and then get the very best hyperparameter and then train on the entire full data set. So you can see on the left that the first very short module is the pre-processing, and then it is the hyperparameter tuning that consists of 5 configurations, and each of them is trained on the full data set. So you can see that it's taking a relatively long time. And on the right, it's first 5 short jobs for hyperparameter tuning because that's on a subset of the data. And then we can train on the entire full data set with the best hyperparameter we configured from the tuning phase. And you can see there is a significant amount of time saved on the x-axis. For future work, the first thing that is the most important is to deploy SI on Phoebe cluster. This is because we cannot have access to GPU resources on GCP. So that's a top priority. And for resource provisioner, that will also be desirable. And in the future, if there's more support on the interface side with the system, that we can capable of doing more stuff. And it's also good to explore more hyperparameter tuning strategies, such as agent optimizations mentioned earlier. But that's maybe not the top priority in our case, because we want to maybe focus more on the global optimization, such as model enabling in the machine learning models and stuff. And also, we might want to explore different data subsample algorithm. Right now, we only support random sampling, but depending on the case, maybe a better algorithm will benefit more for both the efficiency and the accuracy of the model. And not that very important one is lazy data upload, which means that right now we upload all the training data at the very beginning of the execution. But a lot of the scenario is that the data is already resided on the cloud. So we'd better first check which portion of data is already on the cloud and then decide which portion to upload. This is not a big deal when the data set is not that big, but when it's come to large models with huge data sets, it will actually consist of a lot of overheads for our system. And a reflection, first thing first, we need a really good documentation and code maintenance for the entire project, because one significant feature of the side project is that it is a Capstone project that has a great churn rate of students. So a good documentation and maintenance will ease a lot of the onboarding overhead of the student team. And also, we want to achieve good encapsulation and modelization of the program for the use of future modification of the code and adding more features and functionalities. That's what we are doing actually right now to better encapsulate and document everything. And the last part is to plan wisely before the implementation, learn thoroughly about the limitation and of the infrastructure and lower systems, so that you can plan wisely on what can be achieved and what cannot, and to communicate wisely with the team and see what we can get the support. And that's something that we are lacking in our first design phase, because we didn't actually know entirely about what we can achieve with the system at the current moment. So maybe some of the example being our availability of interface to query the available hardware resources. So which led us to quite hard to actually implement the efficient resource provisioning. And also, we cannot get details of the execution logs from outside SDK itself. So it is hard to start from the program itself to actually see what's going wrong and start the error correction process. And also, maybe a flexible job at launch, halt and resume functionality is highly desirable, because if that's being implemented, then we can have actually short-lived the jobs that will keep the container for a long time. And it will be beneficial for our resource provisioning tasks. And that's all for our presentation. Thank you very much.
Great job, guys. A couple of thoughts. I think if you go back to the slide where you compared yourselves to the AutoSK, yeah, this one. So I think the first question is sort of, how did you control what you asked each system to do so that it was an identical task?
So what we did is basically, so AutoSK Learn supported only a limited set of models. So that's why we had to implement decision tree, gradient boosting, random forests, and k-nearest neighbors by ourselves, so we can run it on SI AutoML.
Okay.
So we did that. So it was the same model that's used, and the way we implemented is using scikit-learn itself. So it would be the same model, and everything else would be the same. So in that way, it's pretty fair. And we did not do any pre-processing as well, so that and we asked AutoSK Learn also to know no pre-processing. And the only thing here is AutoScaler had a default parameter saying that it can execute at max for 60 minutes. That's why you see the AutoScaler time to be around 3,600 seconds.
I see.
Yeah, even though we identified a better model in shorter time, we ran another experiment allowing AutoScaler to take like 3 hours to try and find the same, like a better model probably if it ran out of time. But even in 3 hours, it identified the same model. So
I got you. Yep.
yeah.
Very interesting. Okay, so you really set up a great experimental implementation where really the only thing that changed was your tuning algorithm, right?
Yes.
Yeah.
Yep. That
So,
and
so that was the other thing I wanted to ask about. So I think what's interesting is so I wanted to verify. So the AutoScaler number that you're showing here, was that using the Bayesian approach?
yes. So AutoScaler only has Bayesian optimization, and they
Gotcha.
use that.
Okay, so and then your Asai one right now only has that recursive
Yes.
one.
We had
Right.
grid search and recursive, and we used recursive.
Right. So I think then what we can conclude from this is that for the set of parameters that you chose, your algorithm, comes up with a better, outcome, right?
Yeah.
All else being kept equal. So I think you have to have something that's more or less a reasonable, a reasonably convex optimization, right?
Yeah.
Convex, concave. But assuming that you do have the right kind of sensitivity, I imagine that the approach that you're taking, Ruben, is kind of a reasonable one, sort of out of the box to provide with a reference framework. Do you agree with that, or do you think it's not as general as Bayes in some important way?
So like if we're being honest, like in terms of like performance of identifying optimal model, we did not think that we get a better model than AutoScaler because
Okay.
theoretically they do like joint Bayesian with model optimization, and it sounded really good, and I felt that they would do better, but where we would catch up is definitely based on time. So in terms of time, we would be way faster in terms of the pure hyperparameter tuning algorithm as well as the distributed implementation. But yeah, we didn't really expect Asai AutoML to do so well. That's why we reran the experiment and we again got similar performance. So
you're not sure whether this is going to hold up in a more general
yeah, I don't think we can say with like utmost confidence that our hyperparameter tuning will beat their hyperparameter tuning in all settings. Like I don't think we can say that, no. But in terms of time,
but
like
what I find interesting is that for the first models that you thought of to try, there's already this very interesting phenomenon where there's another hyperparameter tuning algorithm that works better. Wow, evidence that we should all be exploring other, alternative models, right?
yeah, that makes sense. Because like we had kind of developed all of this for like QA pipelines and much larger models, whereas AutoScaler only supports like small ML models like decision tree and gradient boosting, which are not so resource intensive. So it's quite interesting that this beats like AutoScaler even with such small models as well.
Yeah, to add up, actually, I look into some of the documentations about hyperparameter tuning in this already on the market model frameworks. And a lot of the people actually commenting on those fancy hyperparameter tuning algorithms, such as Bayesian optimization stuff, actually didn't perform as good as a simple one, such as grid search. So it's rather interesting in this sense.
Yeah, well, I think the what really matters is what the epsilon is, between the performance you get with the grid search and the performance you get fiddling around with Bayes for a while, whether it's worth it. And maybe in a lot of cases, it's not worth it. Yeah. Okay, anybody in the room have any questions?
Yeah, Why were you thinking about building your own auto provisioning system when there is one that exists already in the SI systems model?
Yeah, in that regard, we don't know actually that much about the provisioning on the lower end systems, but right now our handle to tune around with the resources is actually the vCPU and the memory that we can tune around with that. And actually that has a huge impact. I don't know if we specify that through our code, where it stick to that with the lower end system.
We should talk to the systems team, but I would say absolutely it should.
Yeah, then like for that, these two parameters, when we tune around it, actually it has a huge impact on our performance of in terms of how fast we can train our models. So there's actually something that we can do from our end. And also we also based on our decision based on the observation that actually we know more information about what we want to do in terms of the jobs on our higher end, because we know exactly what jobs are similar and what stuff, and these are not accessible from the lower end system. So in that sense, we
can expand the API so that you can send that information.
Yes.
Say, I know more about my application. Take these recommendations into account as you fulfill my requirements in the execution.
Yes.
Yeah.
Yes.
So maybe we should meet more often.
Yeah.
Yeah. In the future teams can meet more often to resolve these issues.
Yeah.
All right, thank you. I also have one question. You said that the setup of the pods was pretty expensive for some of the runs. This can be resolved through latency hiding. That means you launch the pods earlier, or you have a pool of pods ready to run. We call them, this is the cold start problem. Yeah. So have you thought about that? That you have a set of pods that are running with some base functionality, where you can run some of the green jobs without having to pay all of that orange cost.
Yeah, I think that's a great thought. And we are what we are want to achieve is the start and halt and resume functionalities basically can be fulfilled by that, because we just want to keep some long running pods that will take different jobs and run, and we're not permanent forever. Yeah, but in our real development of our current scenario, like actually we won't able to afford that on our end, because we need to bring up the Kubernetes clusters, and each of that time it takes pretty much a bunch of money.
Yeah.
All
right. Thank you. Great work for making it work.
Thank you so much.
Other questions? All right. Well done.
Thanks, guys. Great job. Really appreciate it.